Hello everyone, welcome back to this online course on fundamentals of composites and cellular materials. So, we have almost come to the end of this course. In today's lecture, the focus is basically to discuss on the application oriented advanced composites. Now, as I have mentioned few times that we have divided the advanced composite topic into 4 classes, and then the first 3 topics we have already discussed, like advanced MMCs, advanced CMCs, and then advanced processing techniques to make composite materials. And now, in today's class, we will discuss on the different applications where advanced composites are being used, like space industry, nuclear energy industry, automotive industry, aerospace industries. So, let us go one by one. The first example which I am giving here, you know about this material by now. Okay. This is a very simple material you may think like aluminum reinforced with boron fiber. Okay. So, we have discussed about aluminum matrix a lot, we have discussed in detail about boron fiber also. If you remember, boron fiber is synthesized by which method? Anyone can remember it? Boron fiber is synthesized by, as you can see from this particular structure of the cross section, this picture of the cross section gives you an idea that actually boron fiber has been synthesized by chemical vapor deposition. You can see here there is a this core which is basically the tungsten wire. So, the tungsten wire boron gets deposited by chemical vapor deposition technique. And we discussed when we were discussing long back about boron fiber, we said that boron fibers, even it is costly to make, however, boron fibers are used in exotic applications. As I was mentioning that boron fiber, they show very good mechanical properties like strength, tensile strength in the range of 3 to 4 GPa, and then modulus in the range of 380 to 400 GPa. So, extremely high strength and very good modulus. Okay. So, these fibers can be used to as it says here, the application of aluminum boron composites in most heavily loaded dynamic constructions, then where there will be requirement of high load carrying capability, boron fibers are used. Okay. So, you can see here and what kind of mechanical property we achieve once you reinforce aluminum with boron. You can see that aluminum, what is the modulus of aluminum? In the range of 70 to 72 GPa, only that. However, when you mix with boron fiber in the range of 60 volume percent of boron, you see 266 GPa modulus is actually being achieved. Similarly, strength you see 1400 MPa, aluminum alloy can never reach this kind of strength. However, when you reinforce aluminum matrix with boron fiber, this kind of strength and this value, high value of modulus can be achieved. And how in this particular case, this composite material, as you can see here, this is the aluminum matrix, and then you have this boron fiber, and you can see nicely those tungsten cores which has been used as the substrate while making the boron fiber. Now, how this particular composite material has been made? It has been made by diffusion bonding, and I have discussed about diffusion bonding earlier when we discussed about synthesis of metal matrix composites. If you remember, I would say you can go back to your earlier classes where I discussed about metal matrix composites, synthesis of metal matrix composites. There I have talked about diffusion bonding, just to give you again a little bit of just to remind you. So, what is diffusion bonding? In diffusion bonding, so if you actually if I try to draw it, so there will be these thin sheets of aluminum foils, and then these fibers would be taken like this, and then again there will be thin sheets will be coming of aluminum. Again these fibers will be laid down in this, like arranged like this, again like this kind of thin sheets will be coming. So, there will be multiple layers of thin sheets or basically this kind of foils of aluminum, and then this layer of the boron fiber will come, and then there will be application of temperature and pressure, okay. And because of that this aluminum layer will now actually diffuse in between the boron fibers. So, aluminum metals will diffuse in between the boron fibers like this, okay, at higher temperature, application of higher temperature and pressure. So, we are applying here temperature and pressure both, pressure and temperature, and that leads to this kind of microstructure formation. So, you can see here how nicely aluminum has diffused in between the boron layer and ultimately has formed this composite material. Okay. So, now let us look into some other applications, some real applications, space applications of boron fiber. Okay. So, if you look at this particular picture, this picture is actually the mid fuselage structure of space shuttle orbiter. Okay. So, if you see all this as you can see here, these struts, as you can see all these struts, and also you can see these tubes, okay, these tubular struts. Okay. So, all these have been made by aluminum boron fiber. Okay. So, basically the internal frame structure which has been made here, shown here, mostly made by aluminum boron composite and some titanium. Okay. And that actually gives the enormous load carrying capability, enormous stress bearing capability of these space shuttles. Okay. So, you can see here it says that this BAL boron aluminum tube provides 45% weight saving compared to the baseline aluminum design. So, you can see here there is weight reduction, almost 50% weight reduction than conventional aluminum alloy. Along with that, the strength, the load carrying capability, the stress bearing capability increases to manifold when this kind of aluminum boron fibers reinforced composite materials are used. Okay. So, that is the application of aluminum boron fiber. Let us look into some more applications in space industry. What you are seeing in this picture is basically the Hubble telescope. We all are aware about Hubble telescope. Now, this Hubble telescope will be having this antenna, okay, which basically acts as the receiver and supplier of data. Okay. So, basically that antenna is here, and then antenna is supported by this long, around 4 meter long this kind of, you can see this column. Okay. So, the picture you can see here, a better picture you can see here, this kind of slender rod structure you can see here. Okay. And this is made nothing but by aluminum graphite composite material. So, again this is aluminum matrix and has been reinforced with graphite fiber. So, you need very high stiffness because of this long structure, and then there is a heavy weight supported at the end, top end. So, obviously, it must be having very good stiffness. At the same time, it should be having low weight. Not only that, that means it should be having very high strength, high stiffness, but not only that, another very important application or work being done by this particular boom is it also acts as the waveguide. That means, it transmits electrical signal between the spacecraft and the antenna dish. Okay. So, again you can see that there is no other composite material or other material which can be used here. That is why graphite, it shows very high strength, high modulus. Okay. If you can make graphite at a high temperature, graphite fiber or carbon fiber at a high temperature, it shows extremely good strength and modulus, and those can be used to make this kind of aluminum graphite composite material. Okay. And again this has been made by diffusion bonding, where sheets of graphite fibers and the sheets of 6061 L would be diffusion bonded together to form this kind of structure. Okay. So, again diffusion bonding is being used here. All right, let us move on. We have lot of examples to see. This example what we are seeing here, actually this picture, if you see, this picture is a graphite magnesium truss structure. Okay. Now, here this magnesium tubes you see, Okay. These are all as cast tubes. These tubes are basically reinforced with this tubes goes to a process of filament winding, and then this graphite long fibers would be filament winded on these tubes to give the support. Okay. So, lightweight at the same time extremely good stiffness, and that is why these are used as truss structures. So, graphite magnesium tube for truss structures applications, and this project was initiated by DARPA. DARPA is basically the Defense Advanced Research Project Agency in US Department of Defense. Okay. DARPA and Air Force sponsored technology together they actually ventured into this particular product and successfully prepared this kind of composite material for high load bearing truss structure, where the weight requirement, the weight should be, it should be very lightweight as well. Okay. Let us move into the next application. This one you can see again space application. If you look at this this multi fitting truss nodes. So, you can see there is this is the node actually, there are multiple fits, okay, and these fits are used in this kind of trusses. Okay. This is a very simple structure, but there could be complicated truss structures being used in space shuttles. So, those those multi inlet fitting structures are being made by again different kind of aluminum based composite materials. So, the matrix is aluminum and it could be reinforced with SiC or graphite to give this kind of structure. You also can see here in this case discontinuously forced reinforced cast graphite aluminum composite, okay, which has been used in electrical packaging applications. So, in space industry, when it comes to high end applications, where you need extremely high strength, at the same time you really care about losing the weight, you do not have any option other than going for this kind of composite materials. I will give you some more examples about aircrafts in the end section. Let us move into a new sector, which is nuclear energy sector. Now, nuclear energy sectors, in certain applications we need materials of high temperature strength. At the same time, it would also be showing extremely good resistance to irradiation. Both are requirement. We need some materials which can withstand high temperature. It will be having fairly good strength at extremely high temperature. Along with that, it also should be resisting the irradiation which happens during in any nuclear energy sector, nuclear plants. Okay. And SiC composite material comes handy in those applications. So, you can see here it is hybrid night SiC insulator. That means, night is a particular process by which this SiC composites are prepared. This is basically a nanopowder infiltration and transient eutected process. Okay. We do not have really scope to discuss this method, but basically it is a method by which there will be a precursor, there will be a preform of SiC, and this SiC preform will be loaded with again SiC only to fill it nicely and then get this kind of structure. Okay. Again you can see here heater, SiC heater, and you can see it is working, it is in working condition. Okay. So, and again these are used in nuclear fission reactors. Okay. So, SiC composite material is extremely important in nuclear energy sector. We again have application of SiC composite material, and you can see here these are used in vessel components for high temperature gas reactors, including their very high temperature reactor variants leading to R&D in multiple programs including the US DOE. So, in Department of Energy, where they are trying to make next generation nuclear power plants, in those cases where you need materials, as I was mentioning earlier, which can withstand high temperature, there this kind of and this kind of joints also could be made by SiC fiber composite. Okay. So, again application of composite material in exotic areas. All right. Now, let us come back to our automotive industry. Now, there are lot of applications of composite materials in automotive industry. I will not discuss about all the topics, all the applications, but let us discuss few. So, the application which comes in my mind firstly is this one, cylinder and piston liner. Okay. And here the matrix is aluminum and graphite particle. Now, if you are aware about cylinder and piston liners, these two combinations goes through continuous wear. At high velocity it moves, it slides along each other, and that leads to very high amount of wear loss. Okay. Now, how these are made? If you look at this particular picture, you can see here this is the cylinder and that is the liner, and if you look at the inner core, what you see here that the color is different. So, this kind of material, this kind of structures are made by a particular casting technique which I have mentioned initially. It is called centrifugal casting. In centrifugal casting, what happens? The graphite particles which are lighter, which the density of graphite particle is lower than the aluminum melt. So, during centrifugal casting, what will be happening? Those graphite particles will actually come to the inner portion. Okay. And you can see here the microstructure has been shown. So, in inner portion you can see there is a lot of graphites, and then as you move from the inner to the outer wall, the graphite, there is no graphite. Now, why the at the inner portion the graphites is there, these graphite particles are there? These graphite particles here would be acting as lubricants and will be giving a nice lubrication when it is in operation. Okay. So, you can see here as it says, the cylinder liner can be cast in a single step by centrifugal casting process to concentrate the graphite particles only in the inner periphery where they are needed to provide self lubrication, solid lubrication. Okay. Aluminum alloy cylinder liners containing dispersed graphite particles have been used to provide solid lubricants. It lowers the frictional coefficient and wear rate, and it has been tested in gas and diesel engines as well, and it has been observed that it exhibit reduced friction coefficient and wear rates. And ultimately, you can see here as you use this kind of composite material that enables engines to reach operating temperature more quickly while providing superior wear resistance, improved cold start emission and reduced weight. So, with superior wear resistance, it also provides reduced weight. Okay. Let us move into another example. I have discussed about this. So, let us move on. Again, automotive application in case of bearing. Okay. So, again same kind of application, same kind of fundamental idea is here. In this case, this is actually copper graphite. Earlier, this was used as copper lead in bearing applications. Okay. Because lead provides certain amount of lubrication. However, now it is being trying to be getting replaced by this aluminum copper graphite. Again, by centrifugal casting this has been made, and at the inside core area, okay, inside wall, what you see is that there is distribution of graphite which provides lubrication when it is in operation. You can see here the wear loss has been compared. This blue line is actually for conventional copper lead bearing, okay. And then you can see here obviously with load the wear loss is increasing, but if you compare that with this copper graphite, you can see in case of copper graphite the wear loss is quite low compared to the copper lead system. Okay. And also you can see the slope, so if you compare these two slopes. So, with increasing load the slope does not increase that much, that means the rate of wear also is less when you are using this kind of copper graphite systems, copper graphite bearings. Okay. Let us discuss some more. Connecting rods, it is a very nice example has been shown here. What you are seeing here, it is a, so you can see particular this structure. So, this is basically a 3D weave of carbon fiber or Nextel fiber. Now, you guys remember what is Nextel fiber? I have discussed about it also. Nextel fiber is alumina fiber. Okay. So, using alumina fiber or carbon fiber, this kind of 3-dimensional weave could be made. Okay. Those could be made, this could be like fibers could be woven into this kind of 3D structures, and it will be acting as a preform. Okay. What is preform? You guys remember? Preform is basically loosely bound fibers which will be having good amount of porosity, and these porosities will be infiltrated with molten metals, or in some cases in those porosities, basically those porosities will be filled with some matrix material by different techniques. There are different techniques available. So, the preform is the loosely bound fibers materials which will be containing good amount of porosity, and this porosity will be filled by matrices by different methods. Now, this 3-dimensional preform would be prepared, has been prepared here, and then as you can see aluminum or magnesium has been infiltrated inside that to give a solid structure. Okay. And so, when this carbon fiber or textile fiber is being actually woven to make this kind of structure, it gives almost kind of a finished product structure. The shape of this would be almost like a finished product, so that you don't need too much of machining. And then this preform will be infiltrated with a liquid metal, in this case magnesium and aluminum, and it will be providing very good strength, extremely good connecting rod. As you can see, it moves, I mean it is always subjected to huge amount of fatigue loading. Okay. So, tension and compression. So, there is a huge amount of fatigue loading in connecting rods. So, at the same time we want to also decrease the weight of the engine block. So, this kind of structure would be having extremely good strength, extremely good fatigue resistance, at the same time it will be having also quite low weight. Okay. Another very interesting example of composite material is in automotive industry. Okay. What you are seeing here is a brake. Okay. Now, this brake pads or brakes, these disc brakes are being made by this short carbon fiber reinforced SiC composite. Why this is being used? Because SiC material is having very high wear resistance. Along with that, if you have carbon fiber, that improves the strength, hardness as well as wear resistance to a very high limit. So, that is why this is an ideal material to be used in brakes. How these are being made? Again a very interesting process. As you can see, these fibers, these carbon fibers goes through a resin bath, gets impregnated by those resin, and then those are actually chopped to make short fibers, and then these short fibers are collected and pressed at an elevated temperature. At an elevated temperature, those resins actually join together, and then ultimately once these chopped fibers are pressed together, but not very hardly pressed. So, now those will be having good amount of porosity. Now, these chopped fibers along with the resin will act as a preform, and then it could be pyrolyzed. Now, the resin, what will be happening with the resin? If you remember carbon fiber synthesis, their resins could be used, or polyacrylonitrile could be used, PVC could be used. Those actually goes through a pyrolysis process and ultimately leads to formation of carbon. Okay. So, that is what is happening here. It forms carbon-carbon composite material initially, okay, and then obviously it will be having lot of porosities. So, those porosities will be now filled by silicon by this LMI process, liquid metal infiltration process. Those porosities will be filled by silicon, and silicon at that temperature would react with carbon and will form silicon carbide. So, ultimately what will be having? You have a silicon carbide structure, inside that you have carbon fibers and some carbonaceous material as well. It will be a very tough material, very extremely wear resistant material. All right, let us move on. Let us come to aerospace industries. Okay. So, let us give me some examples on aerospace industries. This picture what you are seeing here, actually this color coding shows what kind of materials are being used in the body of an aircraft. So, you can see it is mostly blue colored, that means these are all these carbon laminates. carbon laminates, or these are also called carbon fiber reinforced plastics, CFRP. Okay. So, you can see mostly these are all, you can also can see carbon sandwiches. Okay. So, mostly the body is being made by carbon fiber reinforced composite material. If you look at this particular pie chart, you can see here only 20% is aluminum, titanium is 15%, some amount of steel, and only 5% of other material is there, but ultimately 50% of the fuselage body of aircraft are actually made by this kind of composite material, carbon fiber reinforced composite material. Okay. Data has been provided here. You can see that Airbus A380 contains 25% composite, whereas Boeing 787 even contains 50% of composite material. And this kind of composite materials are used because aircrafts, they need high specific strength. High specific strength means high strength, but low weight. Okay. So, and along with that, it goes through continuous vibration. When it is moving at a very high velocity, it goes through continuous vibration because of the air pressure, because of the air resistance and all those things. Okay. So, it goes through a huge amount of fatigue loading. So, we need certain materials which can withstand this kind of fatigue loading, and that is where this composite materials comes into picture. Low weight, high strength, high wear resistance, high fatigue resistance. What else do you need? Let us go into another application, again aerospace industry. Here what has been shown that the different parts of an aircraft, a commercial aircraft, and then those different parts are being made by different kind of composite materials. So, how this CFRP, carbon fiber reinforced plastics, how hugely is used in an aircraft, you can see here. So, you can see here the flaps being made by CFRP, okay, carbon fiber reinforced plastics, and in this case this is made by automated tape laying. Okay. Similarly, you can see here this vertical tail planes, okay, again CFRP. Everywhere you can see here, you can see this the tail wing, that is also being made by certain kind of CFRP. So, all kinds of structural components, load bearing components you can see outside, which you can see all these things are actually made by this wing. This is actually glass thermoplastic. Okay. So, glass reinforced plastic, GRP. Okay. This lids, wing lids. Okay. So, everywhere the whole body you can see different kind of composite materials are being used. Okay. All right, and you can see here another very good application is aircraft brakes. Okay. And these brakes are made by, as I showed earlier, carbon SiC brakes. Okay. How these are made here, you can see another technique. Here carbon fibers are needled. Okay. So, basically those are stitched or needled to make a 3D structure which is called preform, and this preform is infiltrated with, so you can see CVI, that means chemical vapor infiltration. So, it is infiltrated with again carbon, and that can be done by different ways. Okay. This carbon infiltration can be done by different techniques. Okay. I am not going to those things and those topics. You can think about having directly depositing carbon, or you can think about pyrolyzing, and then basically you can infiltrate with let us say polyacrylonitrile or polyvinyl chloride or rayon or any other resin, okay, which will be acting as the precursor material with long polymer chains, and then that could be pyrolyzed to make carbon, to convert it into carbon. So, but anyway, ultimately you get a porous carbon composite material here, and then RMI means what? RMI means this is actually melt infiltration technique. Okay. Reactive melt infiltration. Why reactive melt infiltration? Now, if you infiltrate with silicon, as I was saying earlier, this carbon would be reacting with the silicon, some of the carbon would be reacting with the silicon and will be forming as silicon carbide. So, now again what you have? You have a silicon carbide matrix, and in that you have this needled carbon fibers, extremely resistant to wear, and that is why you can see here this rotor and stator, the outer layer of the rotor and the inner layer of the stator, those are actually made by this carbon SiC composite. Okay. And then this application is quite new actually. GE is doing this thing. So, what they are doing actually, they are using carbon fiber epoxy composites to make these aircraft engine fan blades, okay, which you see rotates at a very high velocity. Okay. So, these engine blades needs high strength, okay, and where we do not really care about, I mean where there is not much of temperature, high temperature generation, there this kind of carbon fiber epoxy composites could be used, which would be reducing the weight to a very good limit, okay, and ultimately would be giving fairly good strength. So, you can see here General Electric has been involved in this effort to introduce carbon fiber epoxy composites into their jet engines. I think the name has been not provided here. Oh, here it is provided. G9X, okay, that is the engine, G9X engine. So, it has actually 22 fan blades, and these blades, some of the blades, 16 blades actually made from this 4th generation carbon fiber composites. Not all the blades, but a good amount of blades, because the other blades give the structural strength, but ultimately you can see here what kind of per engine around 150 kilogram weight could be reduced, which is huge. Okay. So, ultimately I have talked about different sectors, like starting from space industry to nuclear industry, we talked about aircrafts, aerospace, before that we talked about automobile, everywhere where we need to have exotic properties like high strength, high temperature strength, high fatigue resistance, high wear resistance. At the same time, we do not want the weight to be going higher to the higher side. We do not have anywhere to go other than coming back to composite materials. With that, I would like to end today's class. I hope you all had an enjoyable time through my classes. In the next class, there will be 3 more classes in this course, and these classes would be on natural cellular solid. So, basically wood structure will be discussed in that particular class, and then there will be 2 more classes on functionally graded composite, again an advanced hybrid material. I think you should know about these materials. With that, I end the class today, and I wish you all the best. Thank you all.